All right, let's take a look at Project One. And when I say take a look at, it's not just going to read the handout. We are going to go through the whole process. Okay, run the program, make the table, make the graphs, all of that. So this will show you exactly how to do it. Project One is a Monte Carlo simulation. This is a great use for parallel programming because it's the same equation, different data values. Monte Carlo is used largely to handle uncertainty. Okay, and we measured this, but we didn't measure it exactly within this. It's in this range somewhere. And then you run some number of the simulations using values within that range, and that lets you compute kind of a probability that something will happen versus something else. Okay, here's the scenario. Now, if you go watch this video, and I'm not going to play it here, but it's only 41 seconds. But it's a bunch of people pouring a box of golf balls down a ski jump and trying to see if any of them end up in the cup that's down on the ground. And I don't think any of them did, probably because they were going too fast. But anyway, take a look at it. It's a lot of fun. We're going to run the sort of the same thing, but a simplified model. So we take a golf ball and we set it down here at the top of the ski jump. Oh, I can click there and make it bigger. And it starts to roll down here or slide down here. Let's assume sliding so we don't have to deal with moment of inertia. This height is called before Y. This height is called after Y, and it's horizontal right there. So it's after rolling or sliding, it's got a certain velocity, a horizontal velocity, and then it flies through the air and gets sucked down by gravity and eventually hits the ground. Okay, that's called after Y. At a distance called dist x, there's a hole. Or if you're playing golf, there's a cup, but there's a hole. And what I'm asking is, what's the probability that the ball actually falls in the hole? Okay. So the people who did the measurements were not exactly good at it. And so they know that the height of the ski jump is 80 feet plus or minus 5. So we know it's between 75 and 85 feet high, but we don't know what it really is. There's a little plus or minus right here. The after Y is 20 feet plus or minus 1. The dist x is 70 feet plus or minus 5. Okay, so we're going to pick random numbers in those ranges and run the simulation, find out if the golf ball falls in the hole. We're going to do this for a whole bunch of times. And from that, we know how many times we ran it, how many times the golf ball fell in the hole, and that'll give us a probability. Okay. All right. Yeah. Okay. If you're a physics geek, yeah, I know. We're neglecting depth effects, and the depth effects play a big role in that video. We're neglecting moment of inertia of a rolling golf ball, not a sliding one. We're neglecting air resistance. We're ignoring the Coriolis effect and the motion of the sun. Yeah, of course. Let's just have fun with this. Okay, so run this for some combination of trials and num trials and vary the number of threads. We're testing parallelism here. Okay, do timing for each combination like we talked about in the project. Run each experiment some number of times. I typically use like 20, and it's in the code. So that you can find out of those 20 trials, what was the peak performance? That's the closest you're going to get to the true performance. So yes, we really would like to do that. Produce a rectangular table and 2 graphs, and we'll go through this in this video. All of this is described in these note sets. So if you haven't looked at those, you might want to just pause this one and go back and take a look at those. Choose one of the runs, probably the ones with the most trials, and tell me what you think the actual probability is. As you increase the number of trials, the number will converge. Choose one of the runs, probably the one with the maximum number of trials, or probably the number of trials, and maybe the most threads, and compute the parallel fraction. The Amdahl notes, okay, Speedups and Amdahl's law tell you how to do this. Once you know the speed up between one thread and some number of threads, then you'll know how to get the parallel fraction. Then also, if you know the parallel fraction, what's the maximum speed up you could ever get? This is also covered in the Amdahl notes, okay? You're not getting it by looking at graphs. You're getting it by using the Amdahl equations. All right, does the ball end up in the cup? Well, coming off the ski lift, here's the horizontal velocity. Here's the time to hit the ground. And here's the distance it travels before it hits the ground. So now you can, and I'll give you the radius, it's in the sample code. Now you know whether it fell in the hole or not. Okay, you're going to need to use the C absolute value function, which is called fabs. Okay, so the code below is, well, it's printed here to make it easier to look at and discuss, and you can just copy and paste it. If you're on Visual Studio, take the comma std error out of the pragma line. And the reason for that is explained in the OpenMP notes. All right, here is setting the number of threads. If you do nothing else, it's going to use 2 threads. So if the numt is not defined anywhere, use 2. But you are going to define it in the script if you choose to hit the easy button and do the script. Same thing here. If you don't use the script, this numtrials will be 50,000. If you do, well, then you're setting it from somewhere. Here's the number of times to run it to get the max performance. This will print out your data in a CSV format. If you copy the, or if you comment it out, you'll get your data in a nice text format. Gravity is 32.2 feet per second squared. Here are the values, and the radius is 3, but here are the values, and here are the plus or minuses, okay, right out of the table. You're going to create values for however many trials you're running. Here is the random number function. Here's the time of day seed. If you call this, this will seed the random number function with, well, the time of day, which means every time you run your program, you'll get slightly different results. Depends if you want that or not. Yep, make sure you've got OpenMP turned on. If it says you don't, go look at the OpenMP notes. It'll tell you how to do that. Set the number of threads in the thread team. And what we're going to do here is we're going to call up all the random numbers. We're going to create all the random numbers. I don't want the random number generation to get into your timing. The timing is measuring compute performance. All right, we're going to run this 20 times to get the max performance. Here is our pragma. And again, if you're on Visual Studio, take this out. Here we're running for the number of trials. Oh, darn, there's some question marks here. Yes, you have to fill this in. Here's the performance in mega trials per second. And if it's greater than the max that we're holding, replace the max that we're holding. Okay, that way we'll get the max performance. Here's the probability. Number of times it fell in the hole divided by the number of trials. If you're doing CSV for your output, it's just number, comma, number, comma, number. Otherwise, there's some nice explanatory text in there. All right, we talked about this. If you want to compile this and run it, just do this, okay? We're not defining anything. We're going to use what's in the code. It'll do 50,000 trials. It'll do 2 threads. You run it like this. If you put all this in a make file, then it's a little easier. You can say make and the target name, and it will type that line in for you. Or in a script. And notice what the script is doing. It's got a loop up here for how many threads to use, and a loop here for how many trials to use. Okay, and this minus capital D is essentially it's creating a pound define. So numt is now going to be defined as whatever number here you're using at the moment. And trials is going to be pound defined as whatever number here you're going to be using. So you can, let's see, there's 5 thread combinations and 1, 2, 3, 4, 5, 6, 7, 8. That would be 40 combinations. So you can edit, compile, and run your program 40 times and write down the performance numbers and all. Or you can do this, which will take about a minute. So yeah, yeah, you can pick an hour versus a minute, up to you. To run this, you'll say bash, that's the name of the script language, loop.bash, that would be this file. Greater than ampersand means take all standard output and all standard error and put it to here. Poof, there you go. Okay, turn in process. You'll do this on Teach. Teach is expecting 2 files. One is your CPP file. The other is a PDF report. Has to be PDF. Our script looks for PDFs. Put your title, your name, your email address at the top. I concatenate all these PDFs together. And so if you don't put your name there, we don't know who we're grading, and we can't assign you the points you earned. So yes, help us do that. You need to have a rectangular data table, and I'll show you how to do that, and 2 graphs, and I'll show you how to do that. You need to put in an estimate of the probability. You need to estimate the parallel fraction. Okay. And then you need to put a little commentary. Why do the graphs have the shape that they do? Well, that's up to you to tell us. And here's how we're going to grade it. All right, that is the project. Let's go onto the computer. If I look at the make file, yep, there it is. The first line in a make file is the target. And here's, if I want to make the target, here's what I need to make it. And then any lines after that is, well, if I have proj01.cpp, here's what to do with it to make the file or make the target. I can just type this in, this G++ line, and it'll work. Or I can say make proj01, and there it goes. Okay, and if I want to run it, /proj01, and it's in CSV format. So 2 threads, 50,000 trials. There's the probability it got, and there's the mega trials per second performance. Now, what you probably want to do is not run one, but run a bunch. So there's the loop.bash. I've added some more trials in here to create more points on the graph, but it's essentially 2 nested for loops. And so it's going to run this, well, in my case, 60 times, each time with a different number of threads and a different number of trials. Okay, so let's run it. Bash loop.bash, and there we go. And it's going to run a little slower when we get up to 1 million plus trials. So notice when we start out, the probability is 0. Well, if we only run one trial, either it succeeded or it failed, right? And in that case, either the probability is going to be 0 or 100%. But as you run more and more, you get a converging probability. Now, I know what you're thinking. You're thinking, oh, he screwed up. He put the probability in the video. Now we all know what the correct answer is. Bah, wrong, contestants. That's not the right probability. I changed the numbers for the video. So anybody who just writes down 39.2 as the probability, we're going to know that you didn't actually run the program. So don't do that. Okay, so we just ran it with the script and it printed to the screen, but really we want to go to bash loop.bash outputs to, and let's just call it proj01.csv, comma separated values. And we won't see anything until it comes back because it's dumping numbers into the file in the background. All right, it's back. So let me go to the file that's got it. And the neat thing about CSV format is Excel recognizes it as an input. And notice Windows even puts a little Excel icon on it. I'm sorry, this is so tiny. But if we double click on it, we don't have to copy and paste those numbers into Excel. We just double click on it. It knows it as an Excel legal format. And there we are. There's our numbers. Now, we're graphing performance here, so we could just delete the column with the probabilities. Okay, the first thing we're going to do is we're going to put this all in a pivot table because we need this all in rectangular format. Okay, we need to have threads going across the rows and trials going down. We have to get this in a rectangular format for the graphing. You can copy and paste it, and what a pain that would be. But I'm going to show you how to do the pivot table thing. So first thing we do is we're going to put column labels. So here we're going to say threads, and here we're going to say trials, and here we're going to say, oh, mega trials per second. Okay, now we're going to sweep over everything, including the column headers. We're going to do a copy, Control C or right click, copy. And then I'm going to say insert. And of all the things you can insert, over here in the left-hand side, it says pivot table. I'll just click on the pivot table icon. Yep, it's a table. We're going to click OK. And it's set up another sheet. So our data is still over here, but it's done this. Okay, now we're going to want to graph. Well, threads and trials are the independent variables. Those are the ones you got to change. Mega trials is the dependent variable. So the independent variables go in the rows and columns. So threads and trials will go in rows and columns, and it doesn't matter which one. And then mega trials per second will go in values. And poof, we have a rectangular table, which is what we wanted. Now, for some reason, you can't plot graphs in Excel out of a pivot table. But what we're going to do is we're going to sweep over this part of it, do a copy, Control C or copy, and then down here, do a paste, Control V. Okay, and this is exactly what we want. These are the number of trials. These are the number of threads. Here is mega trials per second. We don't need this. We want to get rid of that. Now, it says in the project handout, you have to put a table in your document. Okay, let's do a copy, Control C. Let's go over to Word. And we'll do paste, Control V. Okay, there's your table. Now, if you try and change the size of this, weird things will happen because it'll try and reformat everything. So what I prefer to do is over in paste, if you do a paste special and say, I want it as a bitmap image, now it's an image, which means you can change the size all you want, and it's not going to goof with the number formats. So, okay, poof, you've got your table. Let's go back to here. We've already swept over it. Let's do an insert and a graph. And of all the graph types, this is probably the best use is scatter plot. And I like the scatter plot with the smooth lines. Okay, there we go. We have now got our scatter plot. And because we have two independent variables, one of them is the x-axis and one is the colored curves. Okay, that's interesting. This is the kind of little jig you'll get because you're sharing a machine with other people. And so somebody else's code comes in and they swap yours out, and now you get a little goof. Don't worry about it. We know it's going to happen. The rest of this looks pretty good. Small data set size, you get lousy performance because, well, the overhead of firing up threads is dominating. But as you get a bigger and bigger data set size, things level out. So not surprisingly, here's 8 threads, 6 threads, 4 threads. The more threads, the better performance we're getting. We also want to invert the graph. So let me well, I'll tell you what, I'll just hit copy and I'll do a paste. And now I've got another copy of the graph. And the reason we're doing that is if you right click on the border. So here's the border of the graph. I'm going to right click. There is a select data down here. And you click on this button that says switch the rows and the columns. And so now we've got that. Okay. So now it's threads on the x-axis and data set size on the colored curves. So it's the same data, but this is giving us 2 different views, and you're required to have both. Okay, now you can change the chart title to be something more descriptive, more than that, and so on. But I'd also like you to do things like put labels on the axes. That's good scientific literacy. Yeah, you can, if you right click on the axis, you'll get this format axis. Notice here the x-axis starts at a negative number. Well, it shouldn't. Let's make it start at 0. And it goes up to 2.5 million. Let's make it only go up to 2 million because that's all our data does. Okay, so you can reformat the axes a little bit. Anyway, what I like to do at this point is do a copy, click on the border, so you get the whole graph, do a copy, and then run over to PowerPoint and do a paste. Now, again, that's going to have all the raw formatting and we don't want it. So let's do a paste special and say, yeah, let's use an image format because now it's an image. And if we change the size, yeah. The reason I like to bring it into PowerPoint is if you want to do things like axis labels, you can do that. We'll just type in we'll do a text box. Maybe we'll center it. Maybe we'll make the text smaller and we'll just put it where we want it, like that. And if I want to make another set of text for mega trials per second, you can just grab that little circle and, oops, and make it vertical and put it where it belongs. So I like to put all the decorations on in PowerPoint just because it's easy to do. And now if I pick everything, Control A for select all, and do a copy, Control C, and go over to the Word document and do another paste special. There we go. There's our graph. And because it's an image now, we can resize it and make it fit in with our text and everything. So don't forget your name and email at the top. Don't forget your commentary. Okay, 1 table, 2 graphs, and commentary. Why do you think the curves look this way? Little zigzag things like this you can ignore because, again, I think that's just the load on the system. All right, so that is how to do Project 1, and that's how to do automated things to put your report together. So really, you can get the report, the details in the report done in about 10 minutes, or you can take a couple hours of doing it. You can sort of pick. But please, I really recommend you get used to the whole scripting and pivot table thing because we're going to be doing this all quarter.